We're going to be covering exponential graphs, and you might recognize that word exponential. Maybe you've heard the term exponential growth before. For example, say we had two bunnies that fall in love, and they have some baby bunnies, and then those baby bunnies have some more baby bunnies, and those baby bunnies have more baby bunnies, and then the bunnies take over the world. There's bunnies everywhere. Run, run! So when we're talking about exponential graphs, we're basically thinking of two things. Either something getting really, really big, really, really quickly, or something getting really, really small, really, really quickly. The general form of an exponential equation is just like this. Y equals ax, a to the x power, where a is any number and x is your variable. As x increases, y is going to get exponentially bigger or smaller depending on what this number is. Now there are a few different ways to graph exponential functions, but we're going to go ahead and do it the old-fashioned way by making a table. Remember, making a table can always give you a picture of what any graph looks like. So here we've got y equals 2 to the x. Let's start by taking the x values, -2, -1, 0, 1, and 2. You can pick any x values, but these are usually a good base. So if we plug in -2 for x, we get y equals 2 to the -2. Now keep in mind, remember, when you have a negative exponent, we could flip that. We could take the reciprocal and change that to a positive exponent. Doing that, we'll get y equals 1 over, taking the reciprocal, 1 over 2 to the positive 2, or 2 squared. And that's going to be 1 over 4. 1 over 2 squared, 2 times 2 is 4, 1/4. So on our graph at x equals -2, the y value is 1/4. Taking our next x value, -1, y equals 2 to the -1 power, changes to y equals 1 over 2 to the positive 1, which is going to give us a value of 1/2. From there, moving on to our 0, we get y equals 2 to the 0 power. Anything to a 0 power is going to be 1. Going to our x equals 1, we get y equals 2 to the 1, which is just 2. Lastly, y equals 2 squared, 2 to the second power. That's 2 times 2, which is 4. Now that we have our table filled out, all we want to do is plot these points just like we always do when we make a table. So our first point's at -2, 1/4. That's going to be somewhere very small right in there. Then we have -1, 1/2. -1, 1/2. That's somewhere around there. Oh, let me just move it about there. Then we've got 0, 1. We've got 1, 2. And we've got 2, 4. Now, if these aren't perfect, it's okay. We're just sketching this out. We want the general shape. And it looks like the graph is going to be getting really small. It's going to trail up, and it's going to start getting really big, really fast, like we've talked about. If you wanted to do more points because you weren't sure, you're free to do so, but it looks like we know the general shape, so this will be just fine. Let's try this one. Y equals 1/3 x plus 1. Start with the x value of -2. That gives us y equals 1/3 to the -2 power plus 1. This negative exponent means we want to take the reciprocal, which is going to be y equals 3 over 1 to the positive 2 plus 1. From there, we've got 3 squared, 3 over 1 squared, 3 times 3 is 9, plus 1, and a final value of 10. Okay, I went ahead and did the next value, -1, 1/3 to the -1 power reciprocal. That becomes 3 to the positive 1, which is 3 plus 1, 4. Taking x equals 0, we get 1/3 to the 0, which anything to the 0 is 1, blah, 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 1. Then we get 1 plus 1, which is 2. Taking x equals 1, 1/3 to the 1 power is 1/3 plus 1. Now you could write that as 4/3 if you got common denominators, but I like writing 1 and 1/3 because it's easier to graph. X equals 2. Y equals 1/3 squared to the second power plus 1. That gives us 1/3 times 1/3, which will be 1/9 plus 1, which would be 10/9 or 1 1/9. Now plotting those points, we've got a -2, 10 right here, a -1, 4, a 0, 2, a 1 and 1 1/3, and a 2 and 1 1/9. It looks like we've got something going from really, really big down here, and it looks like it's getting smaller as we approach this point. And if I just draw that in as best I can, whoop, it looks like it's going something like this right here. Now you might notice, or you might ask, Mr. Zonker, why didn't you draw this getting really, really small close to the y value of 0? And actually, there's a good reason for that. And this is actually going to be getting really, really close to 1. And we call that, when something approaches a line, we call that an asymptote. We're not going to deal a ton with that, but you'll kind of get the hang of these in working with similar types of problems. And the reason for this here is since we have this plus 1, even if this gets really close to 0, we can never get smaller than 1. So it's okay if you don't completely understand that, but it is something interesting to take note of. All right, I'm not going to do this whole problem, but I did want to point out something interesting about it. Y equals 4 to the x plus 2. This plus 2 is a part of the exponent. So for example, if we plugged in x equals negative 2, we're going to get y equals 4 to the negative 2, plugging that in, plus 2. This is all still the exponent here. So we have to go ahead and do negative 2 plus 2 before we know what to do with the 4. Which, negative 2 plus 2 is 0, so we actually have 4 to the 0 power, which would be 1. So I'll let you finish these up, but if you have something adding or subtracting from the exponent, keep in mind that whole thing represents the exponent, and you need to take care of that first before dealing with your base.